Okay, let's try this again now. Make sure we don't bump this thing too.
There we go. Okay, so anytime you want to find the range of a transformation, this is your go-to formula. Okay, so have you guys already calculated these for me? What is t of 1, 0, 0, 0? 1 and 0. You're just putting in 1 for A and 0 for B, C, and D into that formula. So you're just going to get 1 and 0. Okay? How about t of 0, 1, 0, 0?
Negative 1.
Negative 1 and 2. Okay? What about 0, 0, 1, 0? Negative 3 and 0. And what about t of 0, 0, 0, 1? 0 and 1. Okay, great. So does anybody know what the span of that is?
1, 0, 0. Mark that one.
Okay, if I'm asking for the span of something, I'm not asking for a vector. I'm asking for what is the span as a set. R2 is the right answer. This is equal to R2. Now, the thing is that you have actually 4 vectors here. So, but then at the end of the day, what did we decide that the dimension of the range was?
2.
Yeah, the dimension of the range is just the dimension of R2 is 2. So this is one of those places where I have to remind you to be careful that when you have a vector space that is the span of something, don't assume that the dimension is equal to how many vectors you have. You guys can clearly see that the third vector is a multiple of the first vector. It would create a linear dependency, right? And also the second vector could be expressed using the first and last one, right? So really your basis for R2 is sitting right there, your standard basis. But if you had put this into a matrix, remember how you put each vector into this matrix like this, whoops, and then if you're testing for linear independence, you augment it with zeros. Guys, if I give you more vectors than the dimension of the whole space R2, remember W is R2. So if I give you more vectors than 2 vectors, you know they are linearly dependent. So your basis for the range of T, oops, I shouldn't be writing in blue. Blue is supposed to be for things that were not correct, but this is correct. So the basis for the range of T is 1, 0 and 0, 1. Or you can take any other basis for R2 and it will also be fine. Remember, vector spaces have lots of bases. And if you were to, actually if you were to row reduce this matrix, which it already is, you would realize that columns 3 and 4 lead to free variables. Those free variables in turn mean that you have linear dependencies. Anytime you have a wide fat matrix, more columns than rows, right? Remember that little table we had in chapter 4 where the dimension is n and I give you k vectors? If k is bigger than n, they are definitely LD. So these 4 vectors here are not going to be a basis for the range of T. You have to throw away the linear dependencies. So as it happens, this matrix is telling you to throw away these 2 vectors and keep these 2. And that would have been fine as well, right? As long as the 2 vectors that you end up with are linearly independent, there can be many right answers. Okay, so we got that. Now let me just go back for a second. We did earlier, and I guess it got erased, a basis for the kernel of T. If you remember, that one was, I think it was -1/2, -1/2, 0, 1, and 3, 0, 1, 0. Okay, do you remember that before we did all of this work, I asked you if you could figure out a basis for the range of T without actually doing this work here? Does anybody, in thinking about it more, does anybody have an idea why I said that? Why I said that you would have been able to know that the range was R2 and that the basis you could choose this? We could have done this a while back. And I'm wondering if anybody, you can't always do it a while back, but on this problem you can. Anybody know what I'm getting at here?
You transform this basis.
No, I'm saying is it, oh, you mean these vectors?
Yeah.
Well, no, if you transform these vectors, you're gonna get 0. Because these are in the kernel. Yeah. So I'm looking for something else. I'm looking for a fact or a result that is really important that we talked about. Anybody know what I'm thinking of?
Column vectors?
No. Does anybody remember anything about the dimensions of the kernel and the range?
They add up to,
It's the generalized rank nullity theorem.
oh, yeah.
Yes. This is worth, apparently this was good to review, right?
Years ago.
Does anybody remember what those two numbers are supposed to add up to? Remember the result? What number do they add up to? It's got to be a number.
Oh, the number column.
Okay, if I only give you this, there's no matrix here. Remember that? Or maybe not. The dimension of B. We covered this right before the second test. So go back to about March 23rd and check your notes on this, that this is important, right? This is a very, very nice result. In the problem that we are just working on right now, what is the dimension of V? 4. Right, 2 by 2 matrices is 4-dimensional, right? And we found out that the kernel was, what's the dimension of the kernel? 2. Okay, so then this range of T, we should have already known that it was 2-dimensional, right? But on the other hand, if you remember what is the transformation, here it is, right? So this is your whole of W is already 2-dimensional. And if the range of T is supposed to be 2-dimensional, then they have to be the same thing, right? In other words, that's why we could have already said that we already knew that the range was the whole R2. Because the dimension of R2 is 2. The range has dimension 2 also. So it has to be that space. If the dimension of the range was only 1, let's say the kernel was 3-dimensional, and then the range was only 1-dimensional, then we would have work to do. Then we would have to figure out, oh, it's only 1-dimensional, what's the basis for it? But if I know that the dimension of my range is the same as the dimension of my whole W, well, then the range of T has to be W. Has to be the whole space W. Which is what we ultimately found anyway. We figured that out here. We did the whole calculation and we figured that out. What I'm saying is we could have already known that just from comparing the dimensions of the spaces here. Okay, so this might be worth looking back at. There's going to be more examples you can look at in the midterm 2 materials, the review packet and so on. So just thought I would throw that out there. Okay? Everybody all right with that? Okay. You're very quiet. Pondering this. This is a generalization of. I don't have a problem for this right off the top of my head, but this is a generalization of the idea that the nullity of a matrix plus the rank of a matrix is equal to the number of columns of the matrix. So this is another formula that we should have known. This one is for an M by N matrix. So if you have an M by N matrix, of course we learned how to find the basis for the null space and a basis for the column space, right? And basically they add up to M. They add up to M. Again, another way to think about it is the rank is the number of pivots of the matrix. The nullity is the number of free variables in the matrix, which is just the unpivoted columns. So you have n columns total. Each of them is either pivoted or not pivoted. So you add up how many of each you have to get the whole number of columns n, right? But then it turns out, you guys remember, so if I have a transformation, this is something from section 5.1, if I have a transformation from Rn to Rm, then that transformation, if you remember, it always has this type of a structure. It's always just a matter of taking an m by n matrix and multiplying that by the x, which is from Rm. I'm sorry, x is from Rn. X is from Rn. Notice this is an m by n matrix. X is an n by 1 column. And the result of that multiplication is an m by 1 result. So then the point is, so what is the kernel of this? It's the null space of A, right? So that's why the kernel matches up. The dimension of the kernel and the dimension of the null space get lined up. They're basically going to be the same thing. On the other hand, the range of this transformation is just the column space of A. And the dimension of that is just the rank of A. So, so those two numbers have to add up to n. This is something that's near and dear to my heart, guys. Be sure, if you're not clear about this rank nullity thing, or sort of the kernel range relationship, you need to study it. It's a very likely thing that I'm going to ask you about.
Can you repeat that about the whole space?
So the column space is the range of this transformation. Okay, the range, and I did this exact example in class. I probably wrote it down 2 different times, once as a recap and once as an actual presentation. So it'll be in your notes, but the column space of the matrix is the range of T. Therefore, the dimension of the range of T is just the dimension of the column space. And what's the dimension of the column space? It's just the number of pivots in the row echelon form of A. And the number of pivots is otherwise called the rank. So if you have a transformation from Rn to Rm, it's going to give you a matrix here. I don't know. Let's just say, make something up here really quick. So 2 by 4, right? So after you've row reduced that, remember how to do this? You row reduce the matrix. If you're asking for a basis for the column space, you take the pivoted columns and you go back to the original matrix and take those columns as your basis. Right? So in this case, it'll be these first 2 columns that are going to end up having pivots. So your basis for your column space for this matrix will just be 1, 5 and 2, 6. Those 2 columns are what you'll end up with after you row reduce the matrix. That's where the pivots are going to be. So it's a 2-dimensional column space because there's 2 pivots, so the rank is 2, right? And the number of unpivoted columns is also 2, which are the 3rd and 4th columns. And it adds up to 4 columns, and it's 4. Okay? So that's all I'm trying to say here. But then this matrix then gives you basically a transformation from R4 to R2. R4 to R2. Okay. That's just if it's a transformation from Rn to Rm that we can make this matrix association. I can also do transformations that have polynomials in them, or calculus functions, or some other kinds of vectors. And in that case, I'm not trying to associate a matrix with it. But if we're talking about transformations from Rn to Rm, then there's always a matrix that can be associated with it. So if, for example, if I give you, maybe I'm going a little overboard with this, but it's okay. If I give you a transformation from R3 to R4, and it's, I don't know, something like this, 4y plus 2z, negative 3x, and then 2x plus y plus z. Right, there's a transformation that takes something in R3 and spits out something in R4. we will be able to write down a matrix representation of it. I asked you guys to do this in a lot of homework problems already. Basically, it's 4 by 3, right? So it's from R3. So this T goes from R3 to R4. So the N is 3 and the M is 4. And the way it really works is each one of these slots gets a row. So the first row has 1x, no y, and negative 3z. The second row has 4 y's and 2 z's. And the third row has negative 3 x's. And the last one would be the 2, 1, and 1. And there's your matrix representation. It's pretty easy to write that down. Okay, so, no questions on that? You guys comfortable with that? Okay, that's kind of in the beginning of chapter 5. All right, enough on that. Let's go on to another problem. What number am I on? Probably 5. Or 6 maybe? 5, okay. Just kind of want to mix it up because I'm a little tired of linear algebra right now. So I'm going to go back to something else. Talk about another example. So let's do the following problem. Let's solve y prime minus 3 over 2x times y equals 6 times y to the 1/3 times x squared ln of x. Okay. Take this problem. Can you tell me where in the semester this problem is coming from? It's way back at the beginning, right? Those dark days of January, the start of the semester, we were talking about first order differential equations, right? And there are sort of 4 kinds of first order differential equations. And which one is this one? Yeah, this is a Bernoulli equation. It's a Bernoulli differential equation. Let me remind you what the form of it is. Bernoulli equations always have this form here. Right? They almost look linear. If there was not this y to the n here, then what you would have in what I show you there is linear. But the power of y showing up on the right side makes it not quite linear. But what the Bernoulli equation does is we do change of variables to it that will make it become linear. So it's not linear right now, but we're going to make it linear. And the purpose of reviewing one of these kind of problems is that we're not only going to review how to do the Bernoulli equations, but we're going to remember the linear equations too, and how you do the integrating factor and all that good stuff. So I thought this would be a good one to review. Okay, so when you're solving a Bernoulli equation, there's 2 things that you absolutely have to get right. One of them is what is the correct change of variables. So does anybody remember the formula?
U equals y plus 1 minus.
Justin's got it down. That's exactly right. U equals y to the 1 minus n. In this example, what is n in this problem?
1/3.
Yeah, the power of y, as you can see from the right-hand side, is 1/3. Let me also remind you that if there's a coefficient in front of the y prime, you need to divide it down first, because the form here of the Bernoulli equation requires that you've got y prime isolated with a first power on it. So it's already in that form, so we're in good shape here. So this is the first thing you need to make sure you know. So this is y to the 1 minus 1/3, which would be y to the 2/3. Okay, and we're not going to use that right away, but we're going to set this on the side, and we'll use it at the end of the problem when we're going to solve for y. The next equation, which might even be even more important to remember, is what does this Bernoulli equation turn into when you implement the change of variables that I just gave you? And here is the answer. It becomes u, or does somebody else happen to know what it is? Anybody remember this? Jocelyn?
I don't know. prime
Uh-huh,
plus
Yeah.
1 minus n
uh-huh,
u
times p of x times u, yeah.
and then other ways.
Hey, can anybody help with the right-hand side? Q of x, exactly. And the y to the n is gone. The whole point here is that the y of n disappears when you do this change of variables. So I don't want to go through rederiving that right now. That's too much time and effort, but this is the equation. You really want to make sure you know this one here, okay? So with that in mind, what I'm going to do is apply the change of variables to the problem that we have in front of us right now, okay? Okay, so let's take a look at this. So what we're going to get is u prime. Now, by the way, notice that p of x is negative 3 over 2x. So negative 3 over 2x, but then I have to put in 1 minus n. 1 minus n is 2/3. So I'm going to be multiplying by 2/3. So it's actually going to cancel the 3 halves, right? So minus 1 over x times u equals, and again, 1 minus n is 2/3, so it's 2/3 of what's on the right side. 2/3 of 6 is actually 4 x squared ln of x. So that is what you're going to end up with. Okay. Let me just do it real fast. Okay. All right, and now what you have is sort of starting over with a new problem, but this time it's now linear. It's linear at this point. So we can kind of forget what we did before, and we just want to think about it as a linear equation. The way that you solve a linear equation is by using what? Right, integrating factors here. So the integrating factor, the general formula is the following. You integrate p of x dx, and the p of x is, of course, the coefficient of what is now u. So this is not the same p of x that we started off the problem with. We're now looking at this particular one here. So in this case, it's just going to be e to the negative integral of 1 over x dx, right? Don't forget this minus sign. The minus sign is part of p of x, right? Okay, so then when I integrate 1 over x, of course, I get ln of x. Do we need to put plus c on the end of this integrating factor? Not at all, so we'll just leave it as a plus 0, basically. Okay, and what is that going to simplify to when you reduce it down? Yeah, x, basically this minus 1 goes upstairs. It's like x to the negative 1, and then the e and the ln cancel. So it's just 1 over x. We're doing this fairly quickly. I'm hoping it's kind of review. This is the integrating factor. Now what happens is when you multiply this equation through by that integrating factor, on the left side you end up just getting the integrating factor times your unknown function as a product rule. So the unknown function right now is u times the integrating factor, and then on the right hand side you just simply multiply through by the integrating factor, which means you're going to cancel one of those x's. So this is what you end up with. Okay. So in general it's just integrating factor times unknown function derivative equals q times I, right? That's basically what you're going to end up with. The whole purpose of the integrating factor is to try to make the left side look like the derivative of a product. Okay. What do I do next at this point here? Exactly, I integrate both sides. So on the left, I of course just cancel the derivative off. I just get 1 over x times u. On the right hand side, 4 is a constant. The integral of x ln of x is actually in the table of integrals that you'll have. And so you don't need to worry about it. Let me just tell you what it's going to give you. It is going to give you 1/2 x squared ln of x minus 1/4 of x squared, and then plus c. Plus c on the end of everything. That's what it is. Okay. So what is u equal to? Well, I just have to multiply through by x now. So if I multiply through by x, I'm going to get, let me just multiply the 4 all through it as well. So 4 times x would give me 2x cubed ln of x minus x cubed plus cx. Okay? Is that my final answer? What do I still need to do? Replace the u, exactly. So I know what u is. U is just y to the 2/3, right? So this is y to the 2/3. So if I want to know what y is, what do I have to do? I have to take the 3/2 power. Let's say it that way. So I have to take the 3/2 power of both sides. So I'm just going to put a big, huge 3/2 power on the end of this, and then everything in the middle just stays the same. So if I take a 3/2 power of a 2/3 power, those exponents cancel out, right? So you're just going to get this. That's it. That is the answer, I believe, that I got. Yeah, that looks good. Looks good. There are some situations where it's just impossible to solve for y. You get things that are kind of messy and just involve functions that you can't isolate y, or the y appears in several places. If that happens, then it's perfectly okay to just give me an implicit solution, which means you don't actually solve for what y equals. Here, of course, I hope you could do that. You can solve for y very easily. It's not a problem. It's usually on the ones that are either homogeneous or separable, where solving for y can sometimes be hard, but not so much on the Bernoulli and linear ones. Okay. Questions on that?
For the c of x, would it be wrong if we set the c of x equal to c sub 1 and put that in there?
Right, you don't want to do that, because c1 is a constant, but c times x is not a constant. If the x is there, it shouldn't be replaced with a constant. Yeah, so I would just leave it as c times x. If you want practice on the changing the constants and stuff, don't forget you've got, I wasn't going to go over this very much today, but don't forget, what's this the equation for? That's Newton's law of cooling, right? And it's a good example of a separable differential equation. So if you remember, to solve this one, you want to separate it and get the capital T on one side and the little t on the other side, and then integrate both sides. When you actually solve for t, and we actually did this, t of t turns out to be t sub m plus, I think it was, I usually used a c2 because we had changed the constant at least twice before we got to that expression. But this is a good one to review. I know there was one year when on the final I gave people this and asked them to rederive it. So it's just a application of the separable type of differential equation. I wasn't going to spend much time on that today just because it's just integration basically. But, okay, we good on that? Good on that one? Okay. Let's try another example. I guess I'll go back over here again. Number 6. Stick with the differential equations theme for a little bit. Number 6, let's solve y double prime plus 9y equals 18 times secant cubed of 3x. Okay? Give this a try. So when you look at that, what thoughts do you have?